I'm Jody Hagins, and I'm going to attempt to give you an introductory tutorial that goes from introduction to advanced in 90 minutes on Boost.MP11. And, oops, I have to turn it on. So first, I want to explain why this talk even exists, especially with this title here. So why Boost.MP11? Well, I gave this talk last year at CppCon, and I talked about a framework that used a metaprogramming library, but it was my metaprogramming library, hard to use, very fast, designed specifically to be used for that framework. Emil Derchevsky told me that I should consider MP11. I had played with it before once. I found like probably a bad case with it, but I have a lot of respect for him, so I decided to give it a try. So why A Christmas Story? Well, this is the first comment I got about the title. And no, metaprogramming isn't going to shoot your eye out. But you know, I had a hard time just making time in my schedule to do something. And so with Christmas coming up, there's a game that happens every year since 2015. Oh, you can't even see that, can you? Ooh, we're going to be in trouble because all my code is like black background. Okay.
Let's begin by turning off the lights.
Good idea.
Let's give it a shot.
Yeah. Well. Yeah. Let's see how it goes. Anyway, so Advent of Code is a game that comes up. Yeah, because if you can't see me, that's perfectly fine. Is that better?
Is that light that's
How about?
Spotlight.
That one. That spotlight. Move it.
Can we move one of these or disable one of these? I think being able to see that is more important than seeing me.
I'm trying to make sure we see you guys.
Well, you know what? Let me bring up some stuff. Can you guys read that?
Yeah.
Can you guys read that?
Yeah.
Okay. All right. Great. Okay. Thank you. I apologize. All right. So with Christmas coming up, there's a game on the internet. The guy has a site called Advent of Code, where each day from December 1st to December 25th, you have an Advent calendar, and you open up each day and you get a programming puzzle. And so I decided that what I would do is I would solve the Advent of Code problems each day just using MP11 at compile time. I figured, what a great learning experience and a lot of fun. So why this conference for this talk? Well, MP11 is awesome. It's a Boost library, and it's a tutorial about a Boost library at CppNow, so I figure it's a great conference to be at. A lot of library developers, a lot of people with a lot of experience. And even though there's a lot of library developers, a lot of people with a lot of experience, two of the pieces of feedback I got back, two of the reviewers actually didn't even know about MP11. And so I thought, well, you know what, we should probably have something to say about it. This is the documentation. It's a link to the current documentation. We'll be looking at a lot of documentation to kind of explain things because this is a tutorial. It's not necessarily trying to show you the most whizzy-bangiest things that you can do. But all slides with documentation will be taken from that link. So there's two basic concepts in Boost.MP11. And they are metafunction and a type. So everything else just deals off of those things. A metafunction is a template whose parameters are all types, and that's pretty much the way that it goes. Note that traditional metafunctions, you have to do what I call the two-step type name dance, right? Because you have to do this. Kind of ugly. MP11 metafunctions are basically like alias templates from C++14. But really, there's 6 concepts, 4 basic ones, and 2 of them that are just, refinements of list. We're going to try and go through these pretty quickly to just get a basis of definition. Oh, and you can't see that either. Can you see that word right there?
Metafunction, yes.
Metafunction? Okay, great. So a metafunction is a class template or an alias template whose parameters are all types. So a type trait alias from the standard library, a type trait class from the standard library, an NRA class template from the standard library, a fixed 2-element type from the standard library, even something that you may not think of as a metafunction, but remember the definition. Any class template or alias template whose parameters are all types is a metafunction for our purposes. So these are all MP11 things. We'll talk about them. But if I tell you they're metafunctions, there's one thing you can know. Either they are class templates or alias templates whose all parameters are types. And it doesn't really matter what it yields, right? It can yield something that's not a metafunction. The name itself is what we're considering is a metafunction. And it doesn't matter how many type parameters it has, just that they're all types. Note that integral constant is not a metafunction. And the reason is because it has a non-type template parameter. F3 is a metafunction, even though what it returns is not a metafunction. Then we have the concept of a list. A list is basically any template that has parameters of all types, but it's the instance of the template, not just the template itself. So all of these are lists. All of those are metafunctions, as we saw previously. But when they're instantiated with types, then they become lists. And note that a list is basically the invocation or instantiation of any metafunction, since it's the class, i.e. the type, that results when you instantiate a metafunction with type arguments. So a quoted metafunction is basically a class that has a nested metafunction with a specific name, fn. The name has to be fn in order for it to qualify as an MP11 metafunction, or quoted metafunction. So these are all quoted metafunctions. The concept is that if metafunctions all have to take type parameters, well, how do you pass a metafunction to another pure metafunction? Or how do you even bind them, right? So this is the way that you wrap up a metafunction in a type so that it can be a class. So an integral constant type is a class with a public member value. Any class with a public member value is an integral constant type. So an integral stood integral constant, or a struct with a static, or even the old style enum with value. As long as it has a value that is a constant that you can get to, then it's considered an integral constant. A set is basically just a list with all the types unique. There's no special set designation. Any list, which means any template with type parameters, if all the types are unique, it's considered to be a set. So a tuple, where all the types are different, is a set. A list, where all the types are different, is a set. Even that guy is a set, because it's really that, but then don't be fooled because it's really that, right? And all the types are unique, so that is really a set. A map is a concept. It's basically a list of lists, where every list has to have at least one type, and the very first type of each list is considered the key, okay? And so then that's basically a map. So both of these are maps. They're keys, and for this one, you've got a key of int, and the value is int star. For this one, the key is float, and the value is nothing. And for this one, the key is char, and the value is a char1 and a char2. Note also that it doesn't matter what the wrapper or the name of the list is. This is still a map, because it's a list of lists whose first element is the key. Make sense? All right. So we're going to get on to some advent of code stuff. And normally you're not supposed to read things in talks, but I'm going to read it because you got to get like the advent of code vibe, right? We're solving these problems. So Santa's reindeer typically eat regular reindeer food, but they need a lot of magical energy because they need to deliver their presents for Christmas. For that, their favorite snack is a special type of star fruit that only grows deep in the jungle. The elves have brought you their annual expedition to the grove where the fruit grows. And to supply enough magical energy, the expedition needs to retrieve a minimum of 50 stars by December 25th. Now, although the elves assure you that the grove has plenty of fruit, you decide to grab any fruit you see along the way, just in case. Collect stars by solving puzzles. 2 puzzles will be made available each day of the advent calendar. The second puzzle is unlocked when you solve the first. Each puzzle grants 1 star. Good luck. This is the task that we're going to do each day. We're going to solve these problems. And as you'll see, these problems are data-centric problems. These are not solve this with metaprogramming problems, right? So there are algorithms. We could do concepts, but we're not going to do that because we want to practice and learn how to manipulate types at compile time in such a way that is not like manipulating types that we've all been used to before. So the jungle must be too overgrown and difficult to navigate in vehicles or access from the air. The elves' expedition traditionally goes on foot. As your boats approach land, the elves begin taking inventory of their supplies, and one important consideration is food, in particular the number of calories each elf is carrying, which is your puzzle input. Basically, they'll give you a text file each day with input that you have to parse. They give you a sample input, which is small, and then they give you the real input, which is long, which means that if we're doing types, we're dealing with tens of thousands of types at a time in a lot of these. The elves take turns writing down the number of calories contained by the various meals, snacks, rations, etc. that they've brought with them. One item per line. Each elf separates their own inventory from the previous elf's inventory by a blank line. And that's basically what the data looks like. So the list represents the calories of food. Each group is each elf's calories of food. Okay? You sum them all up. Our task is to find the elf carrying the most calories. And then how many total calories is that elf carrying? Now, each person is supposed to get a different set of input to kind of keep it different. I know that it's not completely identical because I had one problem that I was giving to some guys at work, and they Googled the answer and found that it was the right answer. But the idea is that when you log into the website, you have to actually log in. You get the problem for today. They give you sample input, and you actually download the input file. And then you have to tell them what the answer is. And if you get the answer right, and they go, yay, you unlock problem part 2. And then you get to solve part 2. So today's input, you can see it's 22,200 lines. So there's going to be about 2,200 different types in here that we'll be dealing with. So before we get into some MP11, I'm going to do some background because I want us to have something to contrast with, okay? So we'll spend a little bit of time, but first we're going to look at some traditional programming, right? If you were going to just solve this, you could whip this out in a minute. Assume that our data that we got from the file is in a vector of vector events. We would basically initialize our total, iterate through sum the totals, update our maximum value, and then return the max total, and then that would be the answer, right? But remember, our input is these numbers. What is our input going to look like if we're going to do this at compile time? So I basically, each day I wrote an awk script that would basically go through and generate. I generated data in a little bit different format than this. We'll see it later. But this is much easier to start with. So we've got our input, we've got a type list, and that's our whole file, which is basically one piece of input per line. We've got type lists representing each line where there's the first elf and the second elf and each elf in turn. So we basically have a list of lists where each list is integral constants representing the calories for each elf, right? So if we look at traditional metaprogramming, this is kind of something we could do. We define a size, which is just a size t, some type that we can use as an integral constant. And then our go-to for traditional metaprogramming is template specialization. So down here we have our public member, which is the answer, right? So we've got an fn. It's basically going to execute whatever's up top, return some value. Remember, the goal is to return to sum up all these and then get the max. So our primary specialization is to use recursion. There's our base case. It basically says, I'll take anything and I'm going to return 0. And next is a specialization that takes a type list, whose first element is a type list of some arbitrary number of types, and whose remaining arguments are some arbitrary number of types, which have to be type lists, because if they're not, then it'll fail to compile. And then we yield a size, whose value is the maximum between the value of the first value of the list and the value of all the rest of them, which will be the maximum of all the remaining groups. And next we have another specialization, which takes a type list, and its first item is a size, which is a stood integral constant, whose type size t. And the remaining items are all of the other sizes. And those have to be size t's too, otherwise it just won't compile. And then we yield the size, whose value is the sum of the first plus the sum of all the rest, and we're done, right? I mean, it's obvious. We're done. This works. It yields the right answer. But unless you've done this a lot, this really isn't so easy to read, and it's not so easy to write. So the desire is to use a library. So without a library, this is the kind of stuff you end up doing to kind of do stuff, right? We don't want to do this. So before we get on to Boost.MP11, I want to emphasize this. Enough functional programming to save Christmas, right? And most C++ programmers don't come from a functional background, and so functional has kind of a different meaning. And even with metaprogramming, even though it is, I guess technically purely functional because, it doesn't really have the same type of semantics of designed functional languages. So let's look at how we would do this if we did quote unquote functional type C++ using some things with standard library. There's better ways to do this, but this is just something to talk about. All right, we have a vector of ints that has our totals because we need a place to store them. We transform the input of vectors into a vector of ints. And then because we apply stood accumulate to each one of them to get the vector of ints so that we can get their sum. And then we basically return max element of them, right? It's pretty easy to understand. But what we really want to do is have something a little bit more functional. And so we're gonna write some function here. And what we're gonna do is we're gonna take any collection, and then we're gonna take any optional initial value, whose default is default initialized. And then we're just going to call accumulate and return the result. And then here's transform, where transform takes any arbitrary collection and some callable object, and we get our result, which is basically the result of calling it so that we can have a vector of ints instead of a vector of ints. And then we transform that and we return our result. So it's just a different way of having transform. And here's max element. It takes any collection and it just basically returns max element on it. And so if we were to use those from a functional perspective, we'd end up with something more like this than what we had before. This is much simpler, much easier to read. We basically take the max element, we transform it, but we transform the input by calling accumulate. And that's our answer, right? So that's a fairly simple, easy to read, kind of C++ functional type implementation. So I'm getting ready to show you an MP11 equivalent. So those guys on YouTube, you might want to close your kids' eyes because, you could shoot your eye out. So here we go. That's the MP11 equivalent. Now, we've not seen much MP11 yet. But you could probably read that and know exactly what's going on. And this is manipulating types at compile time. So there's the correlation, right? To me, this is like the mic drop moment for MP11. It really is. It's like it's really cool. You get an idea of functional composition and how we can do things at compile time with types similarly to how we would like to do things with data. Okay. Well, that's nice, but as Scott Myers would say, it's a lie. But it's a convenient lie because MP max element really doesn't have a default comparator. You have to give it one. And so here we'll give it MP less. And there's also, this MP sum thing here. That one doesn't exist either. But as Barry would say, it's a one-liner. Right? It's pretty simple. We'll see it. But still, this is pretty easy to read, right? I kind of think that's kind of cool. So with this in mind, we're going to break down a couple of these because we're going to go through some MP11 concepts, right? You have seen the functions. You can get an idea of what they're doing. We're going to go through them in detail a little bit so you can, because these concepts permeate the whole entire library, right? So first, we'll look at MP max element. First, we notice the parameters and the brief description. Can y'all see that? Okay, good. That shows up better in the code. And note there's two parameters, the L and the P. The L always stands for list. P always stands for predicate. So the first parameter is some MP list. And note this doesn't have to be the type MP list of something. It can be any of those things that we said could be lists, right? You can pass any of those to it. That's one of the other beauties of it. Anything that looks like a list can be treated like one. Then we have the P, which is a predicate, which is basically a meta function that right here gets invoked. It has to have a : value because it gets converted to bool, right? So just think of it as it's any predicate, right? It returns some value that has to be, it has to have a : value on it so that it can then get converted into a Boolean. Because that's wrapped in this template, okay? All right, so MP max element. We apply the predicate P to each of these elements right here, and we yield the type that has the greatest value according to the ordering mandated by the predicate. That predicate is going to order these types. Now, what we're going to do next is look at MP-less, because it's one of these ordering predicates. And we're going to look at actually the implementation, and there's a reason that you'll see in a minute. But first note that MP-less takes any two types. It takes T1 and T2. But it's not just any two types. There's a constraint on them. And the constraint on them is that they have to have : value. They have to be one of these things that they call an integral constant type. And MP-less, I think this is, that right there is probably one of my favorite comments in the whole entire MP11 documentation. No, I'm not going to go there because that'll get into a different topic about signed and unsigned. But here's the implementation of MP-less. It's not just less than, because you really want a true ordering, not the stuff that you get when you actually compare signed and unsigned, at least when you're doing these compile time comparisons. But this gives you, this peak is there for two reasons. One, like most everything in MP11, it's just an alias template, right? That's all it is. And number two, we can see that it does more than just a straight X minus Y comparison. And the reason is because if you want to write something else, like MP greater, which we'll see later, MP greater doesn't exist. But you can write MP greater, but you should write it in terms of MP less. Any operation you write, you should write in terms of MP less so that you preserve these semantics. So let's look at transform. Yes?
Do you know why it can have a default?
I'm sorry?
A default. Why MP less cannot be the default?
Oh, just because it's not the default.
Okay.
Yeah,
it would be in principle.
It could be in principle, yes. It's just not. Yeah. So I have my own header that I include the MP stuff, and then I put my other stuff in. Some of the stuff you see, like MP sum and some of these things, and I actually have a version that has default. Yeah, no reason you can't. So let's look at MP transform. Similar to std transform, it does similar expectations. It takes the first parameter f as a meta function, and then a list. But no, it doesn't take just a list. You see the L ... It takes any number of lists. So it'll do a transform on any number of lists. But what does it return? It basically applies f to each successive tuple so that you're basically applying them to the ith element. Right? So, and it returns, it tells you that it has to wrap these up in something. Well, it returns the name of whatever the first list was that you pass it. So you call transform, you give it a list, you give it a pack of lists. It takes the name of the first one and uses that as the name of the result, and then applies the transform function to all of the list, to the ith element of each list, and then returns that as the result. So here we've got std tuple of void int float, and we call transform with add pointer t on it. And we just get a bunch of pointers added to the types, right? That's what you would expect. Well, L1 is a tuple of void int and float. L2 is an MP list of void int and double. We call MP transform with is same. Is same is meta function with the two lists, L1 and L2. And we get back a std tuple because that was the name of the first list. The first element of this tuple is same applied to the first two elements of each list and the second elements of each list. And then the third is applied to the third elements of each list. Make sense? Transform is super, super powerful. We'll see it a lot. So, and by the way, yeah, please feel free to interrupt me, ask any questions. So lastly, we're going to look at MP sum. It takes a little bit, it's very, very simple, but it takes a little bit of time to explain because we have to explain why it's so simple, I guess. Recall what our data looks like. We've got basically a list of lists of integral constants. So when we transform the input, we're calling MP_sum on each element of the list. And each element of the list is the type of that list itself. And that's really what it boils down to, right? The NP transform with MP_sum on the whole thing is the exact same. It's an equivalent to this, where you got MP_sum of each one of these things. So MP_sum is going to be being called on a list of types. Well, there's this thing, part of MP11. It's MP+. But note what it takes. It takes a pack of t's. It takes some number of types. Well, we're giving it, we want to add up the stuff that is the pack of the list. So how do we do that? We basically need to take a list and explode its pack out and apply it to some other meta function. And there's a meta function for that. And it's called MP_apply. And MP_apply basically applies the meta function of f to the contents of the list. So in this case, MP+ is the meta function f, and I have to look at the screen hard so I can, because we'll go through a lot of these things. The entire list is the L, and then the contents of the list are the T, right? The T dot dot dot, that's the contents of this list. And then we end up with MP+ of the contents of the list. Or another way to look at it is that these two expressions are identical, right? And furthermore, let's consider something else in this documentation. MP_apply is just an alias for MP_rename, which just changes the name. So if we write it that way, and then reformat our code a little bit, and then de-emphasize some of the other parts, we can see that we really are just replacing the name of the list. We're basically swapping the MP list wrapper with the MP+ wrapper. Or more formally, we're renaming the list that has its name changed from MP list to MP+. And this is a fundamental principle behind a lot of the stuff in MP11, which is why I'm spending probably more time on it than anything else. So meta functions are basically just the name of something. And you can switch them around and apply them back and forth willy-nilly. I mean, it really doesn't matter. So this pink type, together with the list and the name, that's the meta function of MP list. And it's an instance of MP list with the types, namely the types MP int1 and MP int2. So likewise, this blue type, it has a list with the name or the meta function of MP+, and the types it has, the T's, are those guys right there. Now, both of these lists are the exact same, have the exact same types, but they have different wrappers, or names, or meta functions. By the way, the term wrapper is my term. It's not in the documentation. The documentation basically just uses meta functions, and it also uses name a couple places, like in rename. So there's MP rename. It basically takes the guts out of its list argument. I was told once that I'm a football coach too, you have to repeat yourself on the important things. So yeah. And putting them into its meta function argument, basically we yield this new entity with the same contents as list L, but with the name of this meta function here, right? So from there, it's trivial to write MP_sum. Now my MP_sum is basically just taking the sum and calling this MP_apply with plus on the list L, because I've got a list of integral constants. I want to sum them up. So I'll call MP+ by applying it to exploding out the contents of L and summing them all up together. Okay? We good? Yes?
How do you encode for the initial value? That is part of the apply. Would use the first element as the initial value?
Yeah, it basically explodes all of these types out. So you can look at it as L of, let me go back here, as this list of MP int1 and MP int2. It's basically going to be the exact same thing as MP+ of MP int1 and MP int2. And MP+ takes all those arguments, and we saw that what it will do, MP+ will just take all the things that you gave it and just take this colon value and add all those things up. The implementation is a fold. Actually, That's C++ 17 version of a fold. This is MP11, so he really wants to have it work in C++ 11. So
Accumulate.
it's an accumulation of the values.
But
Yeah,
the
but-
accumulation
so
has
it's just
an initial value.
Yeah, so
But
this
so
one,
this doesn't work
to
for an
apply,
empty list.
yeah,
Yes,
for empty
exactly.
list.
I'm sorry?
It will not give you 0, let's say, for an empty list.
You know what? I have to go look at the definition of
MP plus has a special case.
I think it does. Right there. See right here? MP plus of nothing is NPN 0,
All right.
right?
Yeah, because every time that you do these recursions, you have to think about the base class.
Correct.
The base case.
Yeah. And so when it's empty, it's just 0. I am skipping over a lot of details because I'm just trying to give the overview of a lot of concepts. And you'll actually see in a lot of the implementations, there's probably better implementations, but my goal is to actually give a survey of almost all of the big things that are in MP11. So but no, good question. So we have our MP sum, and then there's our just another look at our solution. Okay? Any other questions?
How long does it take to compile?
That's a good question, and I actually have a bunch of slides with all the compile times, but I think they got pulled out because I was trying to get time. This one right here, actually, of all the 5 that you see here, they'll all compile with thousands of types in well under a second. Yeah, actually, MP11 is really efficient. There's only a couple of places where it has a couple of issues, but it's super efficient. I would say I have actually changed. I use MP11 for everything. If I find a performance problem like I do in normal programming, then I'll go address that one thing. But other than that, it's awesome.
No, but the compilation times are the Grinch on this Christmas story, okay? 'Cause-
Well, not yet. Though there are some later, right? Like there's like day 12 is hill climbing, and I actually implemented Dijkstra's algorithm at compile time with MP11. And after an hour of running and 300 gigabytes of RAM, I decided to stop and then optimize it so that, But all of these thousands and thousands of types, they're still a second or two to compile. No, this problem one, I mean, it takes like literally 0.2 seconds or something. So let's go on to part 2. And I'll probably move on because I'm a couple minutes back, but we're good. So by the time you calculate the answer to the else question, they've already realized that the elf carrying the most calories of food might eventually run out of snacks. So to avoid this unacceptable situation, the elves would instead like to know the total calorie carried by the top 3 elves. So we're not going to read all of this because we're just going to get to the bottom. We want to find the top 3 elves carrying the most calories. So basically you want to take all the list of them, group them by 3s, right, in groups of 3s, and then figure out what the max is of those, right? So assuming our data is in the same format, if we provide a modified sort like we did before, that basically just takes a collection and takes some predicate and we sort it and return the collection. And if we provide a function called take that basically has a number and the collection, and we copy only those number of elements out and we take them, similar to, I think there's a ranges take. And then we return that, then we basically end up with this answer, right? We call transform with the input over accumulate. We sort them, and then we, with the predicate greater, because we want them sorted by maximum. And then we take the first 3 elements and we accumulate them. And that's pretty simple.
Technically, there's also partial sort that can be used.
Yes. And actually, you don't even need partial sort. You could use nth element because all you really need is the ones that are left. And I collapsed all my slides because I actually implement partial sort isn't implemented in MP11, so I kind of implemented it. They do implement nth element, but nth element in MP11 returns the nth element, whereas nth element in stood nth element returns nth element. You get nth element, but you also get the less ones over on this side. So, but MP11 does have partition. So with the combination of nth element and partition, you can basically implement the same thing. And I actually have slides for it. If we get done in time, which I doubt, we can go over them. But so that's our answer for part 2. And that's basically our answer for part 2 using MP11. right? There we go. We transform the input by accumulating the sum of each sublist. We sort the results in descending order, and we take the first 3 elements of the list, and then we sum them up. And there you go. There's another mic drop moment. I mean, for me, because you have to remember, I was playing with this, and for me to come up with this, I was like, my jaw hit. I wouldn't say I was astounded, but I was very pleasantly surprised that I could do this, and it was very cool.
Okay,
Yes.
How do you extract the answers from the compilation? From an error?
Oh no! Actually, what I did is I just wrote a print. So these are basically integral constants and lists. So I have a generic out their types. So I just have in generic overload on stream for a list that'll just iterate through the list and pop them all down. And if it ever comes across an integral constant, it just prints the integral constant out.
So you say at runtime.
At runtime, yeah.
You run it
Yeah, well, it compiles,
and runs.
and then it just has an answer. And so it's like, you can actually look at the assembly, it's like the answer is 10, or whatever it is, right? Yeah. Yeah, so it's all done at compile time, but then to print it out, and I will say that as I'm doing this, generating those streamers is very important as I'm building some of these more complex up, because I want to see each step, what am I getting? And so, as you build it up, it's much easier to just put it out. And what I do is I take it, the output, it gets printed out, and then I pipe it through claim format. Because otherwise you just get this big, huge thing.
You can generate an error or a warning for the compiler and see
Yeah, like
after
link
compilation.
Yeah. But I and a lot of times I'll just, even the big ones, some big ones, I'll put into a file. Okay? So we're going to go on to day 2. And the elves, they begin to set up camp there on the beach. And to decide whose tent is closest to the snack storage, a giant rock, paper, scissors tournament is already in progress. So basically one of the other elves, he goes, hey, thanks for doing this. I'm going to give you a cheat sheet. So he says, look, the first column is what your opponent is going to play. A for rock, B for paper, C for scissors. The second column, suddenly the elf is called away to help with somebody's tent. So you basically have to assume that, the second column is what I'm supposed to play. The winner of the tournament is the player with the highest score. The total score is the sum of your score for each round. The score for a single round is the score for the shape you selected. So 1 for rock, 2 for paper, 3 for scissors, plus the score of the outcome. 0 if you lost, 3 if it was a draw, and 6 if you win. Since you can't be sure the elf is trying to help you or trick you, you need to calculate the score as if you would following the strategy guide. So in here, if in the first round, your opponent chooses rock, which is an A, you should choose paper. This ends in a win for you with a score of 8. And then it just goes through the list of how to do this. But we get the idea. So our goal is, what would your total score be if everything goes exactly according to your strategy guide? Now, it's pretty obvious here. What we want is to basically just be able to simulate each game and sum up the results. Very simple in traditional programming, and even from a standpoint, there's an algorithm to do rock, paper, scissors, right? And I honestly, in the back of my mind, I was thinking, because part 2 is always related to part 1, I was thinking, part 2 is going to be rock, paper, scissors, lizard, Spock. But it wasn't. So here's the input that we transformed. So we basically have a list of lists with their rock and my paper, right? It's just a list of their choice and mine. So the entire file is just represented as a list. Each line of text has 2 elements, their choice and my choice. And so let's implement our solution. We need a couple of things. So MP11 provides a couple of helpers for us for MP constants, MP int and MP size t, that basically just return constants of those types. And so we're going to define some helpers with some names so that it's a little bit easier to navigate. We'll use these as an implementation for both parts. So what I did is I put the common implementation in class day 2, and I had class day 2 part 1 and day 2 part 2, and they just inherited from them so they could use those things. So this represents the score of the choice, which is dependent upon what you chose, and the choice is X for rock, Y for paper, Z for scissors. And then it's also dependent upon the outcome of the game. So the choice score is pretty simple. We basically just cheat. We subtract X and add 1 to get the score, because it happens to be the rock, paper, scissors, and the score is 1, 2, 3, or whatever those are. They're relative to it. And so the losing score is just the choice score plus 0, The draw score is the choice score plus 3. The win score is the choice score plus 6. And next, we just need to define some types to easily identify between their choices and my choices. And so we see this thing here called MP constant. That is not part of MP11 because to implement it in a reasonable way, you need auto, which C++11 doesn't have. So it's easy enough to write. Basically, it becomes an integral constant whose type is the decal type of the non-typed input parameter you gave it, and whose value is the value of it. And in order to compute the result, we might be tempted to do this, right? Because this is the old thing of specialization. No, don't do that. There's several alternatives. The first alternative is MP-cond. MP-cond is like a switch. Not exactly. Remember, all of them are evaluated, but it's similar. It basically takes this class C, which has to be convertible to value, but it's the condition. If the condition is true, then it's going to return the type that you gave it. Otherwise, it's going to recursively call. And note, if it can't be converted to value, you're going to get a nice SVINA error. It's not going to be a hard compiler error. But note that those R's, it's ... So you can have a condition that's just CT and no else. So if there's no else, then you will get an error. But it allows us to do something like this. If it's 8, you went 8, you went 16, you went 32, you went 64, and then the default case is always MP true, right? You just go through a whole list of things you want, and then at the bottom, MP true spits out whatever you want there. So we could do this. There's just our big condition, and that gives us our stuff. But that's not very satisfying, and I want to go into a different area. Remember, I want to show you several things, so what we're going to do is look at an alternative. If we change this list to look something like that, where each list is a list, where the first item itself is a list, and the second item is the score, well, does this look like something we talked about earlier? Yeah, that looks like a map, because it's a list of lists, where the first element is the key. So we can basically just populate the list with all of the possible games and all the possible scores, and then just use it as a lookup table. And so MP-find does exactly what its name suggests. You give it a map, and you give it a key, and it basically looks up the value and returns the parameter. Now note that it returns the element. So it'll return the whole list with the key and the value. It doesn't just return the value. Well, what about if it doesn't find it? It returns void. Oh, but why can it return void? What if void is one of the types in there? Well, it can't, because the definition of a map is a list of elements where the first type is the key. So it's impossible for a void to be there anyway. So void means, I couldn't find it. So we could make the generation of our list look kind of like this. And then we could end up with a table that's like this, exactly like the other one, but just a little prettier to read, a little easier to write. And our entire implementation for day 2, part 1, becomes this. We basically transform the list by calling score on each one of them, and then we sum them all up, because that's what we really want to do, right? So what is score? We're going to call this thing called MP-eval-OR. So I'll get to it in a minute, but basically what it does is this value, we will map find. We're looking something up, right? If we find it, then we get a pair back, or we get a list back that has something in its first thing. We're looking for the second item. That's our value. And so we have to do this rename though, because remember we made our list hard-coded where it was an MP list. So normally the wrapper of a type doesn't matter in MP11 functions, but in this case, you've put a specific type in the map. So that type has to map exactly to whatever the type is inside as the key. So we have to rename it to MP list in order to get it to map in our key. And if we find it, then we call second. Well, what happens if we don't find it? Then that's the answer we want. Because if it's in the map, we want that score. If not, then it's a draw. Because it's not either a winner game or a losing game. Well, how does this eval-OR work? Well, it takes a type, T, as its first parameter, and then it takes this meta function F, and a variadic number of arguments to pass into F. And so what it does, if invoking the meta function f with the u parameters is a valid expression, then that's the result. So basically it says you give me a meta function and some arguments for it. If that's valid, if that compiles, I will invoke that meta function and return to you the result. If it doesn't compile, then what I will do is return that one right there. So it evaluates that. If that's not possible, then it returns that. Okay? So in our code, mpmap, this mpmap find, it's going to return a list with 2 elements if it's found, if it's a winning or losing game. And it's going to return void if it's not found. And so then, if it's found, mp2 will be valid. If it's not found, mp2 will not be valid because you can't take mp2 of void. It's not a list with 2 elements. And so that won't compile. And so we'll get our draw score. Okay? mp-eval-or and mp-eval-if are awesome. They're basically ways of trying to not have to evaluate everything, right? And to give you an opportunity to be able to put it off till later, or conditionally. I only want to call this thing if it's possible, but I don't know if it's possible yet. So that's really the whole, to show you map and show you eval-or is the whole reason we solved it this way. Okay? And there you have it. We're done with day 2, part 1. Now, I'm going to skip day 2, part 2, because I'm already behind. But day 2, part 2 basically says what we're going to do is we're going to give you a list of what you need to play in order to have a win, lose, or draw. And so what we do is we then just go through and set up a second map. There we go, a map with what we need to play. And in order to get this outcome, I need to play a rock or I need to play a scissors. And we use that map in order to just evaluate the first map. And so that's what we end up with for day 2. Okay? It's pretty much the same thing. There's nothing new in day 2. It's just applying a map a second way. Okay? Any questions? All right, day 3. As you'll see, I wonder how Santa gets anything done. Because these elves, man, they got some issues. So one elf has the important job of loading all of the rucksacks with supplies for the jungle journey. Unfortunately, that elf didn't quite follow the packing instructions. And so a few items need to be rearranged. Each rucksack has 2 large compartments. All the items of a given type are meant to go into exactly one of the 2 compartments. The elf that did the packing failed to follow the rule for exactly 1 item per rucksack. Now, you want to talk about safety. The elves make a list of all the items currently. Yeah, my wife told me to just don't even try to tell jokes. The elves have made a list of all the items currently in each rucksack, which is our puzzle input, but they need our help in finding the errors. Every item type is identified by a single lower or uppercase character. And so basically, you get a list, and it's divided exactly in half. The left half is compartment 1, the right half is compartment 2. There's exactly 1 item that's unique in each compartment. And our job is to find them. And so that's kind of the input we get. And this is how we have to prioritize it. If the item that we found that's unique is lowercase, it's got a priority 1 through 26. If it's uppercase, it's got a priority of 27 through 52. And our job is to find the item that appears in both compartments of each rucksack and then sum up the priorities of them. Okay? So that's kind of what the data looks like. And this is kind of what the data looks like now. So this is actually how I generated most of the data. Actually, a lot of it, I just made one big, long character sequence for the whole entire file. And then have to parse and process through that thing, right? There's a lot of parsing and stuff to do, so I left most of that out for here. But basically, there's 1 line, 1 integer sequence. So that's so that it all fits on 1 slide, but you see what it is. That's the whole file. And then each line is basically an integer sequence of character with each character being whatever the thing is. And so what we have to do is we have to convert these integer sequences into lists of types. Because remember, MP11 wants types. MP11 doesn't want things that aren't types. But we've got an integer sequence. And if you look, this is a type. But we are going to have to iterate through each one of these, and those aren't types. So we need to convert this into types. And then we need to split the input into two parts, find the one item in both parts, get the priority of it, and sum the priorities. Now, as is usually the case, MP11 has something for you already. MP from sequence takes an integer sequence and returns a list where each item is an integral constant that is equal to whatever the item in that sequence was. So there you go. We don't have to write anything. We just call it MP integer sequence, or MP from sequence. So next, we want to split the input into two parts. Well, there's this, MP split. That looks promising. It takes a list and a separator, and it splits the list into two segments at the separator. But we don't have a separator. We want to split it directly in half. Now, we could add a separator and then split on it, but there's another way. Remember earlier, we did MP take? MP take allows us to take. If we call take 3, it takes the first 3 items. Well, MP drop is similar. If you call MP drop 3, it drops the first 3 items and returns to you the rest of the list. So if we wrote our split like this, where I call MP take with half of the size of the list, and MP drop with half of the size of the list, and I'm not worried about the edge case, well, what if they're odd? Because the problem has already guaranteed me that each one is half, right? So I know that now I've got one list composed of 2 lists. The first one is the first half of the data, the second one's the second half of the data. That's it. Take and then drop, and then there's my split. Okay? So now I just need to find the one item in both parts. Well, MP11 has this concept of set. So remember what a set is. It's not a special structure or a special type. It's just any list whose types are unique. And there's not a make set, but there is an MP unique. You can give MP unique any L, which is basically any list. And it will remove all the duplicates for you. And it's actually very efficient in how it does it. So don't be afraid of calling MP unique. So if we split our two things up, and we call unique on the first one and unique on the second one, then we can just call set intersection to give us the value that's unique across the two of them, right? And that's what set intersection does. It takes a number of sets. So it provides an intersection across not just 2 sets, but any number of sets. So it means that we can write this meta function, find unique. Yes?
So unique always returns a set.
By definition, yes.
And in some order?
No. Well, it should be in the order that it is appearing, but I don't know that it's guaranteed to do that. Yeah, it just says the duplicate is removed. I think in experience they're in the same order, but I don't know that it guarantees that. Okay, but I think it basically just goes through and removes them, and so it stays in the same order. But I don't know that that's a guarantee. Okay, so I get an intersection, but remember, it takes one type with these 2 elements. I call unique first, unique second, and I call in set intersection. But what does set intersection return me? A set. Well, I don't want a set. I want the one element that's in the set. So I need to call MP first. Okay? So I get this set with one thing, and I call MP first. So that's fine unique. I mean, we basically have just done, we've uniqueified a list, called set intersection, and grabbed the unique item out of one thing, all right there. I mean, it looks, yeah, okay, cool, but that's a lot of crap going on. That is awesome. So then we need to get the priority for that item. And so remember, this is how we get them. Priorities 1 through 6 for lower letters, priority 27 through 52 for the uppercase letters. That's really simple, right? We basically just compare the value. If it's lowercase, give it a priority starting at 1. If it's uppercase, give it a priority starting at 27. And then we just sum the priorities. And we already know how to do that, right? So hopefully there's something new, right? Hopefully I just didn't show it, right? Well, what about this? This is actually the solution. That looks kind of neat. It looks even neater if you picture it like that. Right? So just think of it like that. we call transform. We'll talk about compose in a minute. But basically what it does, it allows me to take that type T and push it through compose so the type T goes in to MP from sequence. And MP from sequence pops out a list of integral constants, right? Then we pipe that through. Shouldn't have said that. How about feed? We feed that into split, which takes that list and converts it into a list of two lists. We take that list and put it through find unique that takes the two lists, finds the unique item, and returns the one item. And we take that one item, and this is specific too, right? Because I wanted to just show that item. These don't have to be lists, because the item we return now is just one thing. And then that one thing gets fed into priority. And we take the priority of it, and then we basically call sum to sum them all up. Okay?
Can you repeat what priority is?
Priority is just the mapping of the character to a number value. The lowercase letters get 1 through 27, and uppercase is 27, 1 through 26, and then 27 through 52. And then we just sum those up. I think this is awesome. I mean, you can, and all of the things that we had to write before were basically one-liners, right? Each one of these is just a one-liner itself, depending on how long your line is, right? So, but each one of them is pretty simple. And then I've written another one where I've composed them all. Well, let's get on to the elegant simplicity that is the magic of MP Compose. So MP Compose takes an arbitrary number of meta functions and it invokes them in order. It passes the result of the first one as the input to the next one. And then the result of the last meta function in the chain is the result of this invocation. So it's much easier to explain now that you've actually seen it, right? But that's what MP Compose does. Any questions? All right. So let's go to part 2. As you finish identifying the misplaced items, the elves come to you with another issue. For safety, the elves have divided up the groups into 3. Each elf carries a badge that identifies their group, and for efficiency within each group of 3, the badge is the only item type that is carried by all 3 elves. That is, if a group's badge is item type B, then all the other elves will have item type B somewhere in their rucksack. So the problem is that someone forgot to put this year's updated authenticity sticker on the badges. I mean, of course they did, right? We're getting an idea of the elves that we're working with here. So all of the badges, they're also the ones that would probably, merge, even though the code hasn't gotten its +2 on the review. So the problem is that someone forgot to put this year's updated authenticity sticker on the badges. All the badges need to be pulled out of their rucksacks and new authenticity stickers created. So basically what we need to do is go through and find the item type that corresponds to the badges of each of the 3 in the group. So we have to group them by 3, right? Take all the elves, group them by 3, and then within that group of 3 elves, find the item in it that's unique. Okay? Similar. So we still need to convert our data items, but we know how to do that. And now we need to create groupings of every 3 consecutive lists. Well, there's a number of ways to do that. But the way I want to do it is with MP iterate, because I want to show you MP iterate. MP iterate iterates over something, not necessarily a list. Well, it takes a class V, any class. I don't know why V, but it's just some class. It doesn't have to be a list. And it's going to iterate over that thing, whatever that thing is. And as its third parameter, we'll get to the second one in a minute, it takes this meta function R. Now, the meta function R is applied to V. And then the result of applying R to V is applied to R. And then the result of that is given to R. Over and over and over again until it doesn't compile. That you iterate basically is compile time, right? I'm just going to iterate calling these meta functions until the meta function that I'm trying to call doesn't compile. And then I'm at the end of my iteration. Does it make sense? So then, when we're done, we take this meta function f, and we apply it first to v, which was our original value, and then we apply it to the result of each time we called the meta function on V. So then we've got a function that we're applying to everything that we've iterated over. Okay? And then we package all that up into a list and return it. Okay? So this gives us a way to iterate over anything we want, calling some meta function that takes that thing, and as long as it compiles, the output will be stored, and then it'll get called again until you can't call it over and over again. Think of it like if R were like cooter in Lisp, right? If R basically just popped the first thing and gave you the rest of it. R would be called successfully until it got to the end of the list, and then it would fail. And then you would call F on each of those elements, on the whole entire list, and then on the list minus the first one, and then on the list minus the second one. And then you'd get a list back with all of those. Very, very powerful function. Very powerful. The only thing I don't like about it is that it's hard to optimize. MP fold is really nice. MP iterate can be a little bit slow. So here we have our meta function. We give it our list. The R here is basically MP drop, right? That's our R, MP drop. We bind it. We call bind. I didn't think I had to go through bind. We bind MP drop with MP int. And notice we call bind back. There's an MP bind, and there's an MP front, and there's an MP back. And MP front takes any variadic number of types, and it'll bind it to the front of whatever meta function gets called, right? MP back does the other. It binds those things to the back of whatever meta function gets called. So MP drop takes as its first parameter a list, and it takes as its second parameter an integral constant type. So we're binding 3 to it. So basically we're forcing it. Any list is given to this thing, it's going to the first 3 elements are going to get dropped. Okay? So we're successively going to drop the first 3 elements. And then we're going to successively take the first 3 elements. Right? And so then we're going to have all of our lists in our group. And so the next thing we need to do is find the one item that's in all 3 lists. Well, we've seen something like that before. We've seen find unique. But instead of extracting sublists here, we want to call back to our friend apply. Because this is basically the same thing we had before, right? Up here, we're manually taking the first thing, calling unique on it. We're manually taking the second thing, calling unique on it. And then we're calling set intersection on them. That's exactly what this apply does. It says, hey, I want to apply set intersection to the transform of MP unique on L. So this list L, MP unique will be called on every one of them. If it has 2, it's equal to that. And then we just apply set intersection to it. Because remember, set intersection takes a variadic pack of types. But what we have here is going from transform is going to be a list. So we call apply to explode that pack out and give it to MP set intersection. And then we call first on it. Right? So there we have it. Now we just need to get the priority, which we already know how to do. And we need to sum the priorities, which we already know how to do. And there is our solution to part 2. We basically transform each item of the list, L. We create a list with each of these groupings. We call transform on it, and we call compose, our magic pipe operator, right? And we take the result of that, send it through find unique, which finds the unique item of the 3 lists, push that through priority, and then we sum them all up. Okay? So by now, I hope you're starting to feel like, where are the types? Right? Where's the specialization? Where's this metaprogramming stuff that I've seen forever that I don't like? And, according to the survey last year, half of the people aren't allowed to use more than 17 in their jobs. Right? I mean, I think this is pretty cool. You can actually write some nice 17, you can write some concepts that you can't do from 20 in 17 with MP11, and it makes it really nice and readable. Okay? Because of time, I'm going to skip 4. There's the solution for day 1, and there's the solution for part 2. I'm going to go to part 5. Okay? And so I kind of started slow, going through stuff. Here's where I start running. Okay? I don't think I'm going to refer to any documentation. We're just going to show you one-line metafunctions to build some big, huge, complex thing. Because in this next problem, I'm not going to read all of them here. I'm just going to show you the picture. There's the picture. That's the input data we get. Okay? We get a file with all of those things. Okay? I basically turned them into char sequences. And what we have to do is we have to simulate a crane. This is a stack of crates. That's what the crates look like. Underneath it is a set of movements. I want to move one crate from stack 2 to stack 1. So I'm going to take that one and move it over there. Or I'm going to move 3 crates from stack 1 to stack 3, and I'm going to move them over there. And it actually tells us that we have to put them in reverse order, right? Because the crane can only do one at a time. So if I have to move 3 from 1 to 3, I've got to move the first one first, and then the second one, and then the third one, okay? So this is what we need to implement. This is what our data looks like. So we need to take the top part as the crates, and the next part as the movements of the crates. This is what it looks like when we include our input header file. Nice and readable and kind of cute. It's basically just a type list of a bunch of integer sequences. There's the first ones, the crates. We want those columns, but we just want those, right? Because those are the crates that we have to move. And we don't want them here in columns, so what we're going to need to do, we want these as lists, but they're in columns. Our lists, when we transfer these constants into lists, we're going to have a list of like this. So I'm actually going to have to transpose this. How many of you have written transpose in compile time with templates before? Chris, the only one. All right, it's not super fun. And then we have to take these moves and we have to parse those into moves, and then we basically just apply each one of them. So there's our steps. We're going to parse the crates, we're going to parse the moves, and then we're going to apply each move to the set of crates one at a time. And then at the end, we're going to take the top off of each one, and that's going to be our answer. I mean, simple, right? So how are we going to get the parts of the input? Well, this one's pretty straightforward. We're going to get our crate input. We're going to call MP_split on chars, right? Because remember, the two were separated by one of those charge things. So I split it, and then I get the first one. That's my input, right? Here's what I've learned, what MP11 allows me to do. It allows me to do at compile time what I do for normal runtime programming, where I break things up into small chunks. It's hard to do that in traditional metaprogramming. You can do it, but you still end up with small chunks being small chunks, right? So this is quite nice. That's it. That's the whole first part. I've parsed the input and got my crates. Next, I need to convert from these integer sequences to type lists. Well, we've done this before too, right? I'm just going to call transform on and use MP from sequence. Well, now I need to transpose. So this is where we spend all of our time, right? Because we have to write this huge transposition. That's transpose. That's it. That's transpose. We use apply to break something out, and we transform. We're calling transform on with a list, right? We're applying list to our big list. Well, let's go back and look at transform again. Remember what it does? It returns to you a type that's named with the first list, and then applies each one as the ith element. It takes a meta function, an arbitrary number of lists, and applies it successively to each tuple. This part's no surprise. Because if we transform list ABC with this meta function foo, we get a list with foo applied to A, B, and C. If we transform two lists, then we've got the list with ABC and the list with lowercase abc, and we get back a list that has foo applied to each of the elements in turn. Okay? So we called transform on two lists with 3 elements. And we got back a list with 3 lists of 2 elements. I mean, this is transpose. That's transpose right there. Now, if you were writing this in production, you would want to do a couple of things like make sure you preserved the name, because right now they're all just going to be MP list. That's an exercise for you to do. It's actually not that hard. It's just another line of code, right? It's not that hard to do. Did I see a hand?
Yeah. I was trying to check. Did transform enforce that all of the lists have the same length?
No. You can give it multiple lists. You can call a transform. It depends on what your meta function is, I think. Right? Because yeah, it'll take them. You can if you call transform, because you can transform. Yes, yeah, you know what? Thinking about it, I don't know. I think if your meta function compiles, then I think it will just compile. But honestly, I don't know. I just started playing with it in December. Yeah, but you know what? Since I'm talking about transform, I should know the answer to that, and I apologize. That's stupid of me to think I could get up in front of this crowd and not know the answer to that. That's an expected question. If Barry were here, he could answer us. But so next, we need to remove these divider columns. I mean, because really that is transpose, right? We just call transform and give it the list, and it's just going to do the transpose on it. So we want to remove these divider columns. So what are we trying to do? We're trying to take this list of 4 lists of 11 things. Think of these characters as the list. It's easier to put them on the screen this way. And we want to create 11 lists with 4 items each, right? And so now we want to remove the dividers. Because remember those divider things. I just want the list. So this is what I want to get. And so before looking at the code, let's talk about this other thing that is a very useful function. MP filter. It takes a predicate, a meta function that is Boolean, and a variadic number of lists, like transform. And it removes all the elements of the first list. And it calls with the ith element of each one. So, and this is pretty much the same as transform. So I assumed that it would probably puke if you gave it lists with wrong number of types. But I did do a transform the other night. I don't remember if it was a pure transform or if it was using something else that had different elements in it. But I'll just keep saying I don't know. That's safer. So note that each predicate uses the ith element of each list, right? Just like transform. And so our remove dividers function, we just call filter. We pass it this MP countif. I don't have to explain that, right? So we're basically filtering on if I have one of those things, one of those things, then I'm just going to filter them. Okay, so that's my remove dividers. So now I have 4 lists with stuff in them, right? Just with the stacks of crates. And now I need to remove the spaces at the top. Remember when we looked at our diagram, we had the stacks of crates and there were spaces at the top of each one? Well, those spaces are still in. So we need to remove those. And so here, those spaces there, we need to remove those spaces, but we should probably also go ahead and remove these numbers because we don't really need them. So there's our remove spaces meta function. It basically just calls MP filter again, the transform on the list, filtering if is alpha. So if any of them have alpha, then those are the ones we're filtering, right? And so then we're just left with the list without the spaces and without the numbers. And now I need to turn this into a 0 index list of crates. Because remember, when we want to move, I want to move 3 elements from list 2. Well, list 2 is list 2. Well, right now, list 2 in my list, it's the first one. It's the 0, 1 one. Well, I want list 2 to be the 2 one. Well, what's the easiest way to do that? Yeah, just stick in an empty list in the front. Right. So I'm just going to push an empty list into the front. And so now the ith number of crates is going to be the ith element in my list. So I've parsed the crates. Now I see, and this is what I get. I still love this, right? Those are very simple meta functions. And now I'm just going to apply these very simple meta functions in order. Apply compose to the type T, and when I apply compose to the type T, I get the raw input goes into get crate input that turns it into this list of crates, calls from sequence on each one of them to turn them into lists, calls transpose to convert the list of columns into a list of rows, calls only columns to get the columns that are now turned into rows, just get those separators out, And then it calls remove spaces, and then it calls listify. And that's it. I mean, this is a lot of complex stuff that's going on, but each one of the steps is actually pretty simple by itself. And then we just put them all together. So given this as the input, this is what we get. This is what we end up with. That's our list. So that's our stack of crates. That's what we're starting with. Now we need to parse the names, or the moves. So a move this many from this index to that index, right? So this is what one of them looks like. And so if we want to do this, we convert from the integral sequence of constant types. We're going to split on a space. So we're split on each one of these spaces. And once we split on the space, we're going to have a list of move, one, from. And in the real input, these numbers are big, right? They're more than one. So we actually have to do the digits. Because I'm just showing you the test input. The input that they give you is much bigger and has more data in it. So they'll have more than one integer here. And then we remove all the words. And then we need to convert the remaining lists into a list of 3 integral constants. And then we'll have a list with 3 things in it. The first one is the number of crates to move. The second one is the stack they're coming from. And the third one is the stack they're going to. So that's easy. It's just like the first one, except this time we're taking the second one, because that's the moves. Next, we're going to split on space. And we've seen this before too. I'm just going to split, but this time on MP constant space. Now I've got a list of lists, and none of them include a space. So then I just need to remove all the words. Call remove if. On that type, if there's an alpha in them. And so now I'm going to remove all the lists that have an alpha in them. And so now, what am I left with? I'm left with just the lists of the individual digits. So I need to convert those into integers. This one is a little bit hairy. I have to call this from digits, and now I'm going to use MP fold. I don't need to talk to you about MP fold because just think of stood accumulate. I'm folding over that list. That's my starting type, the thing I'm accumulating. And that's the meta function that I'm going to call. Now note when I call this meta function, it takes 2 parameters, because the first one is always the state that is being accumulated, and the second one is the thing that you're folding over. And so we're just going to call MP constant on the currently accumulated value times 10 plus the integer value of this digit. And then we're basically going to just convert these things into a number, and we're going to return it. And that's it. So next, and this is basically just the picture of it, which of course I like looking at it like this better. This is just a great mental model for me. So given our test input, here's what we end up with for the list of moves. Just a list of triples, right? And now we just need to apply those to our starting set of crates and apply every one of these to our starting set of crates, and then that's going to be our answer. Well, how do we do that? Well, we're going to simulate our crane. So we're going to call fold over the moves, and MP invoke Q takes a quoted meta function and invokes it. Basically, it's calling the meta function with the parameter. So here, we're folding over the list of moves, right? Because we have our moves quoted meta function that we implemented earlier. Give it the list, it's going to give us the moves. Give crates, which is our quoted meta function, the list, it's going to give us all the crates. And then we're just going to call do move on it. Do move is a little hairy, but it's not too bad considering what all it's doing. So there's our 2 parameters. The first one is the crates, because we're going to fold over our set of crates. Each time we apply a move, we're going to return a new set of crates. And there's our move. And then these are, I actually call these local variables, though that's completely wrong, and people will yell at me for being technically completely incorrect. But when I was explaining it to some other people, it helped, right? Using default template parameters like this, it gives me something to give a name to. And the from crates, the stack of from things, is basically the crates at index from index. And the to is the stack of crates at the to index. And so I'm going to replace from my crates that I was given at from index what I've dropped from the list. And then I'm going to replace that list. So basically, see that I saw some blank stares there. What we're doing here is I'm giving it crates T, which is a list, right? So crates T is a list. Replace says replace this list with that index, right? So the item at that index in the list with that. So here, I'm going to drop this many from the list of the from T, which was the stack of crates I'm moving from, right? So I've got the stack of crates I'm moving from. I'm going to drop that many from them, and then I'm going to replace the list in crates at that index with this list, okay? And so I'm going to then do the same thing. I'm going to replace the list that I just removed the stuff off of the from stack. Now I'm replacing the list at the to stack by reversing. Remember it said you can only take one at a time? So if I want to do one at a time, I just call reverse. And I'm going to take the ones from how many from the from stack because I'm, right? And then I'm going to append to the to stack. And that's it. Easy peasy, right? This is the most complex, this is the most complicated thing that we've seen. It's the most complicated thing we've seen. But it's not that bad, right? Anybody got any questions about this? Yes?
So when you run this to the compiler and you will enable the flag to bring all the types that instantiate, you will instantiate all the intermediate steps, right?
Yes. Yes. Doing the fold, you instantiate the intermediate steps. But fold actually has an optimization. MP fold. Oh, it's on the previous slide. MP fold has an optimization where it does the like take a whole bunch of parameters trick, where each instantiation, so it does a whole bunch of parameters at once, so that you don't have an MP fold instantiation for every single one of them. And so that's why it's much more efficient than iterate, because iterate can't do that trick. But fold is actually pretty efficient. Yes, somebody else had a question. Yes.
So the reason that you fold it is that this way each action is applied to the result of the previous one.
Correct. Yeah. So if we look, go back here. There, right? So we're folding over, each move is being applied to the initial set of crates. And every time we call do move, it's basically going to return a new set of crates that then you're going to apply the next move to. Anything else? All right. Then we need to just take the top off of each crate, right? That's pretty easy. So there's our quoted meta function. That's our implementation of day one, right? We just call transform. We simulate the crane. We pop the front off of it, and we get the first of each one of the stacks. And that's our answer.
Pop front is like take one?
I'm sorry?
So pop front and take one?
Yeah, so pop front down here, this pop front down here is because we added that empty list to the front of it. So we take the empty list off of the front, and then we apply first to get the first element of each of the other lists. Okay? Not so bad. And that's what we end up with. And that happens to be the answer. That's kind of cool. So day two basically says that the number that identified the crane was wrong. It's actually a crate mover 9001 instead of a crate mover 9000. And the difference is that the crate mover 9001 can remove all the crates at the same time instead of popping them one by one. So how do we implement that?
Reverse.
That's reverse. We call identity T. Because now we don't need to reverse them. We just leave them alone. So we just use identity T. And we can make it better because we can actually send in a quoted meta function for it, right? And then we can just call simulate crane with bind front by passing it one. And then the first solution can send it MP quote reverse. The second solution can send it the identity function, right? And then we've got the implementation of both of them already. Okay? Any other questions? We got like 5 minutes or so for other questions. Or I can try and go back and show you the nth element, but I think I'd rather just take questions. Yes.
So in this last example, could you have just used filter to get down to the numeric numbers instead of the split on the spaces and
Yes, you could have used filter. Yep.
so there's an equivalent to is alpha that's like is numbers.
No, I wrote is alpha.
You wrote that.
Yeah, I wrote that. Yeah, I had. Yeah, that doesn't exist. I had to write that. The is digit and is alpha. I wrote those.
Okay.
But they're very simple. Yeah.
And why do you need the quote on top of that?
Yeah, because it's a quote. Okay, good question. Because it's a quoted. Oh, you know what? In this case, you know what? The function is wrong. I edited this. This is actually supposed to be a class Q, not template type name. That's wrong. The slide is in error. But the reason we're quoting it is because we're passing them along to another meta function. And if it's this is one of the interesting things, right? So Boost.MP11 is all about meta functions, but half of its API is not meta functions, because by the definition of a meta function, all the template parameters have to be types. But some of them, like if it's underscore C, it takes a number. If it's underscore Q, it takes a quote. If it's not, it takes a meta function, right? Like even the predicate, they take meta functions. And if it takes a meta function, it itself can't be a meta function. It's confusing at the very beginning until you start realizing that a quoted meta function is just a class. But still, even when I wrote this slide up, I screwed that up. But you call, and there's in order to turn any meta function into a quoted meta function, you just call MP quote. And I think we've seen MP quote a couple of times.
So the underscore Q will apply quote to the last.
No, underscore Q. So I had a whole section where I explained all this, and I got rid of it because, yeah. But no, that's fine. It's good to know. So all these functions. So you've got like MP transform. MP transform takes a meta function. You can't overload names by template types, right? So if it takes a type or if it takes a template, they have to be different names. So what you'll see in MP11 is that every single API that takes a meta function has another version that takes a quoted meta function, and it's underscore Q. So in here, you'll see sometimes where I call underscore Q, that has to be a quoted meta function. Transform underscore Q has to take a meta function. This fold underscore Q has to take a quoted meta function, right? So and the reason I had to use underscore Q, because bind always returns a quoted meta function. Bind always returns a type. And so it always has to be a quoted meta function. So, and this was confusing for me at first too. Underscore Q does not mean MP fold Q is not a quoted meta function. It is a meta function by itself. It's not quoted. It's basically saying, I'm MP fold, and the thing you give me needs to be a quoted meta function. It confused me at first. Yeah, and some of these things, but that's fine, because the compiler errors that you get when you confuse the quoted meta functions and meta functions, they're really, really nice. I mean,
Sure.
You only have to do, compile 2 greater than n1, pipe through less, and then search for error colon, right? I mean, it's like literally thousands of lines. But it's not super nice.
There's a bracket missing there. Where we put it?
I'm sorry?
There's a bracket missing, I think. No?
There's yes, there is. Yeah. No. There's one here at the fold.
Okay.
Yeah. Yeah, you can tell this was the last one I added. I spent most of the rest of my time deleting them. Yes. Anybody else? Okay, ask another one then.
Okay. Historical question. So at the beginning we had Boost.NPL.
Boost.NPL at the
You
beginning.
could do all these transformations of types and even
Yep.
integral concepts
Yep.
and all that.
It had a lot of this, yes.
And then people say, okay, but sometimes I need to mix, Python computations with dynamic values. So there was this Boost fusion.
Mm-hmm.
Is there a corresponding thing?
I would say that Hannah would probably be the corresponding thing to this.
NPL and Fusion were very compatible in the sense that they have similar nature. I think HANA is a completely different thing.
It is completely different, but I think the functionality you're looking for is
But
similar. Yeah.
It's like you usually start doing NPL and then you realize I need runtime values and then you switch to Fusion. It's more or less seamless. I think here you invest a lot of time in NP11 and as soon as you need a runtime value, you have to switch to HANA directly.
Well, depends on what you mean by runtime values. I'm doing this with I'm using this with runtime values a
Physical
lot.
Things that you need to map types to values.
Well,
Runtime
yeah,
values.
yeah. Well, you can do that. You can do that too. And there's also some supporting functions for managing types with tuples and doing apply.
Yeah.
There's a number of things in the documentation that provide
Okay, so that
runtime
was my question. Did
adjustment.
MP11 already consider some runtime values that you could insert into this?
Basically, as tuples, as tuples. That's kind of it. As yes.
Okay. Well, that's no.
But
Yeah.
MP11 is only on types, right?
Yeah.
It's not on values. Like Fusion is on values and types.
Yep. Yep. And it does have like those apply functions where you can give it to stuff and it'll.
Yeah, you can have for
Yeah.
so you can get from types to values.
Chris, I saw your hand.
Yeah, I have a question because I really loved in the beginning when you showed the comparison between the runtime world and compile-time world. But at some point, I noticed that you stopped doing that. Was that because it was too hard or it was too difficult?
It was because it was too much. It was taking too much time. I tried to do this. So what's happened is basically since January, we have at Main Street. We have what we call Main Street University, like every Wednesday morning from 9 to 10:30. And so basically from like January or on, I was basically doing these live with the people that are on my team. Anybody that wanted to show up, hey, let's solve these live, and we were just coding them. And so I did a presentation to them, and I couldn't get through it. And they're like, yeah, you need to get rid of a whole bunch of stuff. So that's one of the things that I cut. I did it at the very first, and then I didn't do it for the rest of this.
Okay, and just a follow-up question. So MP11 is awesome. However, it's like getting the error messages. Sometimes it's difficult, and I wonder what was your experience and how you deal with that.
My experience was the error messages are very difficult. Yeah, that was my experience. That it's not. I don't think it's designed to try and help with error messages much at all. Literally, I'd compile stuff, piping it through less, or piping it to a file, and then formatting the file, putting the file through any type of formatter I could, because you get these types that are just huge. And if I could get it to compile, then I would basically just output it to standard out, pipe it through Clang format, and look at what it was giving me and go, oh, that's why, because it's giving me this thing. But yeah, the error messages are not nice. Especially especially if you're using bind and you confuse quoted with unquoted, the error messages MP11 doesn't try to give a whole bunch of error messages. It's got a few of them, but in general, you get whatever your compiler gives you.
Another confusing error message I see it very occasionally is like if you're missing one of the include headers for a particular alias and it gives you some very seemingly unrelated error, but it doesn't give you any hints that it can't find that alias.
Yeah, I struggled with that at first, and so what I did is I just include Boost/mp11.hpp. And I include that in my own, because and so I know that some people don't like the MP underscore. I didn't like it at first either, until I started writing some of my own with my own namespace, and I'll just using namespace Boost MP11, using namespace my MP11 stuff, and I call them all MP underscore 2, like MP constant, and that way I don't really care the difference between them. And I found that I don't really have any collisions with anything, right? And I actually have found that I kind of like it now. But yeah, so I include the whole entire thing. I really haven't seen much of a difference in compilation times whether I include the whole thing or not. And none of these solutions take more than a couple seconds to compile. Anything else? Hand up or nope? All right, great. Thanks very much.